Today we are talking about a great topic. Nanite. We upload a video each Tuesday, so take a second to subscribe, it helps us a lot. And don't forget to turn on the little bell to stay informed about all the new uploads. Now, let's get started. Nanite is Unreal Engine 5 Advanced Virtual Geometry System. But wait a minute, what exactly does it mean? Actually guys, it's not that complicated, believe me. In fact, Nanite simplifies several long and difficult processes involved in creating a 3D object, especially the creation of low-poly models with the baking of maps, such as normal maps, as well as setting up levels of details, LOD. But that's not all. The principle is similar to the system already known and used for 2D textures, known as Mip Maps. It streams the most appropriate level of detail at the right time and place, without being noticeable on screen, all while maintaining good optimization. For textures, it's essentially about adjusting the resolution, but as you can imagine, for 3D objects, it's much more complex. That's the reason why Brian Carris and his team started working on Nanite over 10 years ago. It has been a long time goal, but the technical limitations and challenges were considerable. The aim here is to display the highest resolution quality of a 3D object, no matter where it is in the scene, and especially in relation to the camera, with the highest possible optimization down to the pixel, whether it's with a few or millions of triangles. Previously, we had to use a low-poly model with textures baked in advance via a high-poly model in order to use, for example, normal maps and/or displacement maps. Normal maps are generally used in projects requiring rigorous optimization, such as video games. Indeed, they rely solely on the low-poly model, and the normal map creates the illusion of relief by imitating and replicating the detail originally created on the high-poly model. Normals also help to capture in a certain way how light would react if there were real relief. This is roughly the same for bump maps. On the other hand, we have displacement maps. Using a grayscale texture, we create real 3D relief. This also means that our low-poly model will need to be subdivided in order to deform the vertices correctly, without causing improper deformation. As you can imagine, this method is less optimized for real-time applications like video games, for example. It's more commonly used in cinema and traditional CGI rendering. Here we focus on the details of the mesh itself. If we consider the display aspect of our mesh in relation to its position and distance from the camera player, that's when LODs, level of details, come into play. Using proxies with simplified and lighter textures, this system allows us to change the mesh on the fly as we move away from it. LOD 0 corresponds to the highest level of detail for the mesh. LOD 1 is the lower level, with the texture going from 2K to 1K, for example, and some details being less refined because they are no longer visible or necessary. This continues with LOD 2, 3, and so on. The problem with this system is that the change between LODs is often noticeable, and the proxies replacing the original mesh cast very simplified shadows, often visible to the naked eye. Before that, there's also the culling system. It determines when to spawn the mesh. Then the LODs manage the display based on distance. We've all played video games and noticed obvious culling, right? Well, now you know the technical name. Isn't that cool? In short, optimization comes at the expense of quality. With Nanite, it's simple. You no longer need normal maps or displacement maps, which means you don't need to deal with low and high poly models or the whole baking process. The same goes for LODs. There's no need to generate them or spend time setting them up. There's also no need to manage any culling because you'll be able to constantly spawn the mesh on your scene no matter the distance. Nanite will handle all of this for you in just few clicks, and in a completely non-destructive way. The concept is straightforward. Use your high poly model as is. No need to import your low poly model with normal and/or displacement textures. Your mesh will stream at the highest quality and resolution, whether it's 1 mm from your camera or thousands of kilometers away. This algorithm is simply revolutionary, and I feel like few people truly realize it. Before anything else, and to make it easier to follow this video, let's talk about how to enable and set up Nanite, shall we? First of all, if you're on a PC with a recent configuration, you shouldn't have any issues enabling Nanite in your projects. Additionally, by default, Unreal project settings are now well configured to be ready to use this algorithm without any extra steps from you. We're ready to go without needing to activate anything. Now, enable Nanite on the mesh is pretty quick. One method is when you burn your mesh. This applies only to static meshes, which I'll discuss shortly, by selecting the Bold Nanite option. A quick tip, if you're not using light mask in your project, disable the Generate Light Map UVs option during imports. This will save you optimization time and speed up the import process considerably. If you have meshes already in your project, simply right-click the asset in your content browser and check the Enable Nanite box. Similarly, you can enable Nanite directly via the Edit tab when you double-click on your asset. You'll find the Enable Nanite Support attribute there. If you have a large number of static meshes you want to activate Nanite for, you can enable it quickly using the Edit in Property Matrix feature. After selecting all your meshes in your content drawer, right-click, go to Asset Actions, and click on Edit Selection in Property Matrix. You'll now have access to all the individual parameters of each static meshes in your selection. You'll find Nanite settings and its activations in the Details tab under Nanite Settings. Once Nanite is set up, we'll navigate through different visualization modes which are located under Lit in our viewport via Nanite Visualization. To better illustrate and explain Nanite, let's switch to Cluster mode, for example. Of course, we need meshes with Nanite enabled in our scene, otherwise we don't see anything. Nanite dynamically adjusts the mesh geometry in a way that's invisible to the naked eye. It's as if the LODs are being dynamically applied to the mesh's triangles themselves, all happening without being noticeable because Nanite smartly uses a system based on what we call clusters. With a base of 128 triangles, will dynamically adjust these clusters based on our viewpoint. To visualize this better, if we open a Nanite asset and access its editing window, we can enter the following command, Nanite Stats. This command will display a variety of statistics that are interesting to understand and analyze. Without going through each line, for now, let's focus on the total category. You'll quickly see that, based on our position and distance, the clusters and the number of triangles dynamically change. And if we move far away to a single cluster, we'll return to the basic logic of minimal triangles around 128. The goal is to ensure that the clusters maintain a constant size on screen to keep the triangle count stable at different distances. If we go back to our scene with the command enable, we'll also see that Nanite uses a significant occlusion system, which calculates the algorithm only on visible triangles. This means it processes fewer triangles than the total number present in the scene, even when millions of triangles are actually being used. If you move around your scene, you'll notice that Nanite tries to maintain a consistent number of triangles throughout your movement without drastic changes, as long as you don't have objects taking up a large portion of the foreground or a close-up view focused on a specific area. So if we understand the logic here, we're essentially being encouraged to use as many meshes as possible and to overlap them without worrying too much about precise overlap, which is quite different from what we were traditionally taught. This was actually demonstrated during the Valley of the Ancient demo, where the environment was created without a landscape, using only level instances consisting of prefab static meshes overlapped in a various way, with some overlap that would sometimes make your eyes hurt. But since Nanite is trying to render and calculate only what is necessary, the occlusion here is super important and well managed. However, be careful, this doesn't mean you can just pile up billions of overlapping objects without any regard for order. And this is where we encounter a limitation, which we can observe using the Overdraw visualization mode. This mode allows us to see excessive mesh overlaps, especially with respect to our position and to the fact that they are very close together, tightly packed and near the visible surface area in the final scene. The more hotspots I see, the more Unreal is indicating that Nanite will have difficulty determining what to prioritize for rendering, like whether the top mesh should be rendered or the part of the mesh below. The risk is that, in the end, Nanite will decide to calculate all the triangles in this area because, in the absence of knowing what to display, it does everything. So try this experiment. Roughly duplicate and stack a mesh here. If I focus again on my Nanite stats under the total triangle count, you can see that when I display duplicates and then hide them afterward, the number of triangles can change drastically. This is a sign that Nanite isn't working 100% correctly.
So, Stefan, should we absolutely avoid this?
It's not a disaster either. This mostly applies to scenes that are asset heavy with very closely stacked meshes, especially when dealing with foliage. What I just explained here is one of the reasons why, when using Nanite for foliage, performance is often not optimal as seen in environments like dense forests. Speaking of foliage, allow me to draw a parallel and talk a little bit about this type of asset. Of course, as you already know, the good news is that Nanite still works well on assets like grass, leaves, and trees. But there are some things to be aware of, as there are certain subtleties that can hinder Nanite's proper functioning, as I just mentioned. First of all, this type of asset, or mesh more specifically, is what we call aggregate geometry. These are thin meshes that can make Nanite's job more difficult when, for example, you move away from them and the cluster system struggles to handle dynamic change. The risk is that you'll see your grass or the tips of your leaves being cut off, resulting in visible changes to your scene. There is a solution for this, which is found in the mesh editing window. The Preserve Area option instructs Unreal and particularly Nanite to avoid breaking down this type of meshes too much. Another optimization to understand here is that, contrary to the traditional workflow for creating vegetation, where planes rely on opacity through a texture, here you are encouraged to use geometry to make Nanite algorithm run more smoothly. In fact, masked materials are less optimized than classic opaque materials. By modeling your leaves, you'll gain performance and experience fewer visual artifacts. Basically, forget everything you've been used to doing. This is the evolution of the 3D world, right? Epic doesn't mess around. Despite all its benefits, Nanite does have its limitations. It's not magic, so you can't just smash your head on the keyboard and throw billions of assets with billions of triangles all over your scene.
Are there still other limitations with Nanite then? And what are they exactly?
Yes, there are a few more. The remaining limitations mainly come down to the type of mesh, or more precisely, the type of component and materials. At the moment, Nanite is only usable with static meshes, instant static meshes, including hierarchical, spline meshes, geometry collections, anything related to foliage and landscape grass. However, for now, Nanite doesn't work with morph targets or blend shapes or vertex animation. As for world position offset, it technically works, but it's still in beta and may have some limitations. When it comes to materials, the rules are simple. You can only use opaque and masked materials. As we discussed earlier, you might see a slight performance dip with masked materials. The final limitations are related to rendering, particularly with lighting and ray tracing. Regarding lighting, if you've seen my video on the Lumen guide, you'll know that Nanite and Lumen work hand in hand. One goes with the other, and they are designed to work together. This is why we'll encounter some limitation when using hardware ray tracing, particularly with shadowing. By default, Nanite uses a complex and highly efficient real-time shadowing system called Virtual Shadow Maps. Nanite, Lumen, and Virtual Shadow Maps form the winning trio, and this complete setup is activated by default in any new Unreal project. You can use ray tracing to bypass some issues, especially with console command. And I talked about this in one of my previous videos.
Why might I see artifacts with this setup? What exactly is happening?
Simply put, when Nanite isn't usable, Unreal Engine falls back on an alternative solution based on what's called fallback meshes. Whenever you enable Nanite on a mesh, Unreal automatically creates a fallback mesh alongside it. You can see this when you open the Mesh Editor window under the Show tab. This fallback mesh is a proxy that simplifies the geometry as much as possible based on adjustable parameters available in the right-hand panel. It takes over when Nanite can be used, and that's why when you enable ray trace cast shadows on your lights, for example, you might see these visual artifacts. The rays will hit the fallback mesh instead of the actual geometry. In such cases, remember that the console command r.raytracing.nanite mode 1 is your best friend. Also a quick tip, if you want to export a mesh or part of your asset with Nanite meshes, Unreal will automatically export the fallback meshes as well. Make sure to disable Nanite to get back the original resolution. Those were the main limitations of Nanite, and honestly, they're quite manageable. Compared to its early days, Nanite has become less restrictive and is now available in many scenarios. For more detailed information, don't forget to check out the official documentation, which has been updated with many precise and technical details. The big advancement since Unreal Engine 5.3 is Nanite Tessellation. It's still experimental, but we're already seeing it in use in more and more upcoming projects. Nanite Tessellation allows us to use the potential of tessellation, essentially virtualized displacement, combined with the power and advantages of Nanite. It's revolutionary and will blow your mind. Say goodbye to flat landscapes with all normal maps and hello to landscapes with insane detail down to each rock. Unlike world position offset, Nanite Tessellation will tessellate our mesh in runtime, adding millions of additional triangles to match the detail of the displacement map, with just the right number of triangles down to the pixel. Isn't that promising? I talk about it in several videos, whether it's for landscapes or vertex painting. I explain how to set it up, so feel free to check those out. There's still a lot more to discuss about Nanite, like its combined use with virtual texturing to add even more incredible details to your project. But my goal here was to demystify this algorithm and make it understandable for as many of you as possible, with concrete examples and application issues. Nanite is always in constant development, and this technology continues and will continue to amaze. A big shout out to Brian Carris and his team for providing us with revolutionary tools with unprecedented ease of use. Thank you for watching this video, guys. I hope you've learned something new today and that Nanite is no longer a mystery to you. See you next week for a new video. Ciao!